My name is Beau Walker, and this is WDS 11268 plus 0301. It is a binary star located in the Leo system. We study binary stars because they are pretty key in learning about single star systems, because when the stars interact with each other, it shows us how the gravity is going to interact on possibly our star in the future. It is also a trinary system, meaning that it is 3 stars. It is a short arc binary, meaning that all of the observations that we have taken of it are in a very small area, meaning there is a bit of uncertainty. It was first observed by Christian Mayer. He had many different occupations, and he created the first double star catalog. The AC system was first observed by Dr. Friedrich Schembler, and he first proposed the A, B, and C in the trinary system. To image this system, we used ART, the Athabasca University Robotic Telescope run of Athabasca, Canada. We also used the Skynet Robotic Telescope system.
Alright, so in this slide we have data for the AB star. We have a screenshot from Astro Image Day, which is the astronomy graphing software. So we have on the right a graph with the best measurement of the AB system, and we have our measurement as a red cross in the middle of the green things. So, and here in the middle we have a linear and a curve fit for the orbit. So you can see the curve fit is really good. So here we have for the AC star, and we have the screenshots from Astro Image again. And the AC and the C star is above the A and B stars. It's really high in the image. So we can see that the AC distance is 5 times the AB distance, which is a lot. And the fact we can see the C star has meaning, because if it was too close, we probably wouldn't be able to see it. So here we have a data table from the Gaia-2 database from Vizier. So we have the primary, the secondary, and the trinary stars. And we can see that for the trinary stars, the parallax and Gmag values are really different from the A and B stars. So that can also mean that they're not related or gravitationally bound.
At this point, we can consider the parallax and the Gmag data and how they differ between the A, B, and C stars to reach some conclusions about these stars. So firstly, note that the A and B star have pretty similar parallax, but the C star has completely different parallax. Also, the inverse of the parallax tells us the distance from the star to Earth. So as you can see on this next slide here, that the A and B stars are only 18 parsecs from Earth. However, the C star is 483 parsecs from Earth. That means that the C star is 27 times further from Earth than the other 2 stars are, which also lends credibility to the idea that the A, B, and C stars are not gravitationally bound simply because they're too far from each other. But next, consider the Gmag data, where again, the inverse of these numbers tells us the brightness of each of these stars. Note that the A, B, and C stars don't have that different brightness, but if they were on the same plane, then the C star would be much brighter than just an 11 factor. In fact, it would be closer to 5, which would mean that the C star would essentially eclipse the A and B star, disallowing us to actually see all 3 in the same image. But the fact that we can't see all 3 in the same image tells us further that it's very unlikely that the C star is anywhere close to the A and B star, and therefore it's unlikely that the A, B, and C star are gravitationally attracted. But now let's consider the short arc binary quality of these stars. So, a short arc binary is defined as a star system where we have very little data on the entire the orbit of the star. We still propose a period for it. So, for example, in our case, this period is 32,000 years, whereas the current data that we have for this star currently spans perhaps 300 years. As you can see, the data is very concentrated on one part of it. On the top left here, we have the current proposed orbit based on the different observations of the A and B star. And it's very concentrated. In fact, it constitutes about 2% of the entire orbit that we currently have. This is very, very small, and if we can attempt to provide more periods for this, we see that we can get varying types. So for example, we see on the top right that the data is very concentrated around one point, and we can propose a different period for that. But on the bottom right, the period. It's a completely different orbit fit, and the data is on the top instead, where we have different factors for each of these different fits. The fact that we can have various fits has different implications for us. First, it tells us that we can never be entirely sure of the fit that we have. You can have a variety of different periods that are relatively close, but we will never truly know which one is actually the correct one until we observe the star more. Secondly, we can come up with we don't really know how accurate this type of information is, like how closely they're related in the first place and whether they're gravitationally attractive or not. Where we can then take into account the proper motion data on these two stars and do some statistics on them. Richard Harshaw proposed a method to actually take the proper motions of these two stars and do some stats on them and come up with a factor that tells us the probability that they're actually related or that they are gravitationally bound. So doing these calculations, we get a factor of 0.010. And the fact that this is less than 0.020 indicates that it's very likely that these stars are related or gravitationally bound because they have a common proper motion. So we can take that into account as well. In conclusion, we can come up with a few different things. First, we give it further proof that this is not a ternary system. Although this system was already declassified a while ago, perhaps 20 years or so as a trinary system, we provide more data to the Gaia-2 database that this is not a trinary system, namely through the parallax and 0.08 apart and the GMAG data. Next, we have proof that this is a binary system because of 1, the common proper motion, and 2, the short arc binary various fits that we came up with fairly good fits of R² values. Further from here, we're going to assess the viability of a new short arc binary proposal or a new period orbit. We're going to continue tracking the AB system to see how well the orbit fits and how we can use the new data to create new fits. And also we're going to update the Gaia data with more AC information. Below are references, and thank you.